Okay, thank you very much, everybody, for attending this webinar. And I'd like to thank Frenetic for sponsoring this webinar and providing this venue. Now, this presentation is about limitation of phase shift full bridge converters and improvement by variable inductor. So let me start with a short outline here. I'll start with hard switching in the classical PWM converter. Well, the reason is that I'm going into it because the phase shift full bridge is improving the classical PWM converter, especially what is close to it is the full bridge converter, in that it eliminates hard switching. So to really understand the improvement, we need to understand, first of all, what is causing hard switching in a regular PWM. So I'm going to start with this, and then I'll talk about the basic operation of a phase shift full bridge converter and how zero voltage is really achieved. And then the role of the commutating inductor, I call it, this inductor leakage could be, or additional inductor that is very important in the operation. From here, we can understand why a variable inductor could be very beneficial because the inductor has some limitation, couldn't be too big, couldn't be too small. And if you have a variable inductor, you can adjust it just right. And I'm going to actually demonstrate most of these things by LT-SPICE simulation. So let me start with the regular PWM converter. And I'm showing here a half bridge, which could be a synchronous buck or a boost or a leg of an inverter. It's a universal module in any PWM. Sometimes they use here a diode, but of course, if you like to reduce losses, you use a transistor. And I'm considering the case in which the current is going out. This will be like in a synchronous buck converter. In the case of a inverter, it could be coming out to in, then the whole thing is sort of flipped over, but the operation is the same. And I'm now considering the case in which we're turning off the upper transistor. Here it is, we're turning it off. When we're turning it off, here's the current going down. Then the current in the inductor is continuing, and it is charging or discharging, the way you look at it, these output capacitors. And there is here a self-commutation in that the voltage by itself is moving from the bus voltage when the transistor was on to a lower voltage, and until reaches actually ground, and then this current is passing through this diode. So if I'm considering this upper transistor, we see the current going down. The rate at which it's going down depends on the drive. If the drive is hard and fast, a small resistor at the gate, then it'll go very fast. And if the resistor is large, it'll go slower. Of course, it depends on the input capacitance of the gate. And the voltage itself is changing because we are charging or discharging, as I've said, these capacitors through this current. And depending on the magnitude of the current and the size of the capacitance, we'll have here a slope. If the capacitance is large, then it'll be slow. And if the capacitance is small, it'll be fast. And then depending on the current. Now, we need to have enough current so that this process will actually end to the point that the diode is conducting, okay? But as far as this transistor goes, if I'm looking on it, I see at it, I see the current going down, the voltage going up, and I'm calling this situation a pseudo zero voltage switching. It's not really zero voltage switching, but the overlap could be made very small depending on how fast I'm going down with the current and how slow I'm going up with the voltage, okay? So this is the case of a switching when you have a forward current. Now, once the diode is conducting, due to this current of the inductor, then I can turn on this transistor under a low voltage. So this is the read through zero voltage switching. And then after the off duration, I have to move again to turn off this transistor, so I won't have a through shoot. Then again, I'm turning it off under zero voltage switching because there is the voltage of the diode only on the transistor. So this is the true zero voltage switching. Now comes the devil here, and that is this hard switching, which is the problem. This is the main problem in PWM. And that is because of the following. When this diode is conducting and I have to turn on this transistor again, so as to go back to the powering state, then I'm turning on the transistor against a conducting diode. This is the current of the diode. And as we know, there is this reverse recovery, and this reverse recovery causes a very high reverse peak. Could be very dangerous, first of all. Thirdly, causing a lot of EMI, and also increasing losses. So this is the problem, and this is what the phase shift is trying, phase shift full bridge, but is avoiding. Okay, this situation. Now, how can you avoid this situation? You can avoid it by this trick of changing the direction of the current just before this switching state we are talking about. That is, the current of the inductor is going this way, and if you manage just before you switch back, you manage to reverse the current. If you reverse the current, it's not going through the diode anymore because it's in the opposite direction. The transistor will be on, and then you turn off this transistor under this pseudo zero voltage switching. And you can do it in various ways. For example, you can do it by working at a borderline current mode, which is doing the same thing. And borderline current mode is set up such that at the time of switching, the current will be reversed. In the case of the phase shift full bridge, what is doing the trick is this inductor. So basically, the phase shift full bridge topology is very similar to a full bridge PWM converter, except for this inductor, which has a role and has a function, and the way the duty cycle is generated. Duty cycle is not generated by turning this transistor for a short time and then turning it on, not in a 50% duty cycle, but changing the duty cycle. This will be in the regular way. Here it is done by shifting the phase of the pulses from side to side, as I'll show in a second. So I'm now going to talk about these 2 points, the midpoint, X and Y. Okay, we have these 2 points. So if these 2 points have a waveform like this, X and Y, and it's a 50% duty cycle, but they are the same. So whenever X is high, this is high. Whenever X is low, this is low. Then the net or the difference that goes into the transformer is zero. So you don't have any input. However, if you shift one of them, then you have now a situation, again, you're not doing anything to the duty cycle, we just shift the whole 50% square wave, shift it, then you have a situation in which one, say, X is high and Y is low. If X is high and Y is low, then you have a positive voltage fed, the whole voltage actually, fed to the transformer. And then if it's the other way around, the Y is high and this is low, then it's the negative voltage, that is the reverse voltage is like this is high and this is low, then the reverse voltage is fed to the transformer. So the first point here is that we are generating the duty cycle here by this phase shift. It's very interesting and important to understand that although these half bridges look the same, sort of look the same, they are not the same. I'm sorry, this half bridge and this half bridge. And one, we call it leading, and one is lagging. And the leading is the one that is sort of first. And if you'll notice here, what's happening is that this leading part is responsible for turning on the input, actually, okay? The transition of this one, the up and down, is causing this part to go up, and the down is this part to go down. On the other hand, the lagging leg is causing the end of this on time, you might say D on, and also here it's the end of this. And this means that they are not operating the same because this inductor is actually connected more to one half bridge than to the other. I'll talk about it later on. Obviously, if you change the situation in this Y will be leading, then it will be responsible for actually turning on and turning off this on time of the converter. So let's see now how this phase shift full bridge is operating. We start with the powering mode, and that is when this transistor and this diagonal transistors are on, and we feed the full power to the output. Then I'm showing a diode rectifier. Obviously, you usually like to have a synchronous rectifier, but just for demonstration, that's okay. And so we have here this current going this way, and then we have the secondary, this diode is conducting and providing this power to the output, okay? And this would be when this one is high and then this one is high, okay? Here it is, this and this are high, and then you open this pack here. Now, which is different now from PWM, I am only turning off this transistor, okay? When I'm turning it off, and this will be this transition here, then this is the case of a current carried by the transistor and being turned off. So this is what we call a pseudo zero voltage switching. And now this current is charging or discharging this node here. And from low voltage, when the transistor was on, it actually charges the capacitor up toward this point until, of course, the diode is conducting. And then we are locked to a idle or idling state in which the current is circulating here, actually doing nothing. Before that, let me just point out that what is important again here in the operation is charging this capacitor so that the current, which is a reflection of the output. The current here is a reflection of the output, so you have to have sufficient output current, sufficient load. The power should be high enough, so you have sufficient current to charge this capacitor. I'll talk about it a little bit later, because it has to do also with this inductor. But at this point also, it's important to understand that you can lose this pseudo voltage switching if there isn't enough current at the secondary, which is reflected to the primary and responsible for charging these capacitors. So now this thing is locked. While being locked, very important to realize that the voltage at the output is zero, because now the two diodes will be conducting, and since the voltage here and here is the same, then the total voltage is zero. So we have zero voltage across this inner part here, and the inductor, this is the one that I was talking about and doing the whole job of this phase shift, is now actually causing the current to circulate here. Now, obviously, there is a loss here, but this is part of this, let's go into here, loss because the current is passing through this transistor and this transistor. There's no output at this time. This is this time here. There's no output. And this is part of this no free lunch, okay? This is something you pay, and you have to make sure, obviously, that the losses here will not sort of be too high to cancel the advantage of the soft switching that eventually we are going to get here, okay? So this is very important. Now, if you have an inductor which is shorted, the current theoretically will circulate it indefinitely. However, due to the parasitic resistance of the inductor and the transistors, then it'll start actually going down with a certain slope depending on the time constant. So you are losing some of the current, which is very important because of the next stage. You need this energy, as we'll see later on. So once we are ready to go to again to the powering stage after this T off, in fact, we now turn off this one, okay? This one. Again, this one has the current, and as we turn it off, this voltage, this current is charging again the capacitors, and it's going this direction, the current, because this is how it was to begin with. It was like this, and here it is, right? It was like this, and now I'm turning this on, so the current is going this direction. So therefore, the diode now is conducting eventually, and I can turn on this transistor under zero voltage switching. So I've eliminated the hard switching here that I've shown earlier because I've reversed the current. Now, this reversal is temporary because now we have a situation that the output is zero, there is the current, but notice that on this inductor now, the plus is this one, this point here, the minus is this point here, so the current, the IDT is in this direction, so the current is dying down, getting to zero, and then building up again for powering again in the other direction. Okay? So the trick was to have a certain section of time in which the current is reversed so that the diode will conduct and I'll be able to turn on the transistor in zero voltage switching. And then, of course, once the current going this way, when I'll turn on off this transistor, I'll have again this pseudo zero voltage switching. So by this sequence, I've actually eliminated this hard switching case, and I have either full zero voltage switching or this pseudo zero voltage switching. This is the idea of the phase shift full bridge. Now comes the problem. Now I'm considering the very critical case in which after, let me start here, after we had this circulation, I'm turning off this transistor, and I should have enough energy to move this voltage here from the high voltage to ground by charging or discharging, the way you look at it, of this capacitor. The energy available is not from the output now, is from this inductor only, because the output now is shorted. There's no energy coming from the output. There's no current reflected to the input from this inductor or from the output. So we have to have enough energy here. So the amount of energy that we need in this inductor should be larger the amount of energy needed in order to charge or discharge these capacitors. Now I've written here CEVB squared, and this is the total capacitance. Now these capacitors are non-linear, and it's not just a capacitance at one point, because what is usually given is the small signal capacitance or differential capacitance. We are talking about here about a parameter that is called energy-related capacitance. Now, recently, in recent years, you'll find in a datasheet of transistor information about this energy-related capacitance. That is the capacitance that you can use to calculate the energy stored as a function of the voltage, the end voltage. Okay, you have a graph in some of the data sheets. Anyhow, it's not the incremental capacitance. So this is just the point that what is the meaning of this capacitance. In any case, clearly, you must have enough energy to charge these capacitors, and it means that either the current is high or the inductance is large. Now, the current is dependent on the current that we had in the system just before the whole process started. That is, it has to do with the output power, because we sort of froze this current at a given point. So this is nothing we can control. It has to do with the power level of the system. What is taking into account in the design is how much inductance do I need. Now, if the inductance is too small, then this process will not be completed and will be stuck at the midpoint. I'll show you simulation in the next slide. And if it is stuck, then when the transistor will be turned on, have losses due to discharge of this capacitor, which is not now zero, but there is a certain charge on the capacitor, into the transistor. So I'll have a switching losses due to energy stored in the output capacitor, which is shorted into the transistor, and this is, of course, causing losses and reduce the efficiency. Okay, so this is very sensitive. So this brings the idea that if I like to cover a full range, then I can have here a variable inductor so that I can adjust it. So you may ask, okay, why not put a very large inductor so that it will have sufficient energy for all cases? And the answer is that this is also very bad because it is stealing duty cycle, and I'll show it in a minute by simulation. A too small inductor will not be sufficient for soft switching. Too large will cause a duty cycle limitation, which is also very bad because you need certain duty cycle for operation. So this is the idea and why we can be helped by a variable inductor. Now, there are actually two variable inductors that have been published by me, as a matter of fact. Now, this was published many years ago, 1994, okay, and 30 years ago. And this is a variable inductor that the inductor in the two terminals here, the inductor, and this is biasing. I'm not going into it. There is a video in the YouTube in which I'm explaining this and the other configuration I'm talking about. Now, this configuration was actually used by hundreds of papers in which it was shown that this could be useful in many, many applications, including phase shift PWM. There are some papers. I'm not citing them here. This is not an academic presentation, but this has been actually tested. And another configuration is this one, which is simpler and has an advantages. Again, I'm not going into it. You can see that it's fewer windings, and both can give you a inductance which is changing. That is, as you bias it, the inductance goes down, and you can get ratios 1:5, 1:6 to cover a certain range of inductances. And this was published in 24. There again, there is a video that describing this in more detail, which I cannot do here because we have more information to cover, so I cannot go into this detail of the construction of the variable inductor itself. So now, let's have a look now at some simulation results to demonstrate the thing that I've said and to show really what is really happening. And I've set up a very simple LT-SPICE schematics. Here's the bridge. and it is driven in sort of a phase shift way. This is, in fact, where is it? You have here the phase, okay? And it is generating the pulses, the square wave. This is, by the way, just for measuring current. It's a technique for, in SPICE, measuring, referring the current to a voltage source of zero voltage. Here is the transformer. And in order to be able to see what is happening, I've put the inductor outside. Many times it'll be a sort of a integrated magnetics, you might call, in which the coupling coefficient is smaller than 1. So within the unit itself, there is a leakage, but I've again put it outside so we can see what is really going on here and what is the voltage here. We'll talk about it in a minute. And then I have here two diodes, and I've put a snubber so to damp some oscillation due to the capacitance of this diode and the secondary. And here is the filter. This is like a regular full bridge PWM converter. So I'm going to show, first of all, these pulses here, the gates, and the voltage here, and the current, okay? So here it is. This is what I've drawn by hand, and here we have by simulation. So I have the pulses of the gates, and then I have the output. This P1, P2 is the input to the transformer. Okay, so this is the duty cycle, and this is the current. So notice that we have a current during the on time, but we have also current during the off time, because we have this circulating current in the system. This is this circulating current, which is at a certain polarity, which is maintained until we move to the other side, and we'll see it in a minute. So I'm now considering the issue of soft switching, okay? So what I'm showing here, this is just a zoom of this one. This is a transistor. In fact, it is this transistor, this one. And I'm seeing here the current of the transistor, and I'm seeing here the voltage of the transistor. Now, what you can see is exactly what we said, that we have a reversal of the current during this time, that the current was at certain polarity, and then it goes to the other polarity. So we have a section here that it is maintaining, remembering the previous polarity, which is doing the trick of this reverse current, and then we move on. So here we have a very nice soft switching, zero voltage switching, of course. Here we have a pseudo zero voltage switching, which in the other cases, again, it has to do now with the question, how fast can we change the current, as I've said. Now, what happens if I don't have enough energy? Now, if I don't have enough energy, then the voltage starts going down, and then it'll be stuck because there's not enough energy in the inductor to move it to ground. And then when the transistor is turned on, I'm discharging the capacitance, the energy in the capacitor, the output capacitor, into the transistor, and I'm getting here this spike, which is very bad. So this is what happens if you don't have enough energy. And here I have it in a more illustrative way. Let's have a look here at the zoom part here. This is again the voltage of the transistor for various inductors. So when the inductor is small for a given current, it starts moving, but then it goes down because there's enough energy. If the inductor is larger, okay, then it'll go higher. And then eventually, if you have sufficient, the inductor is large enough, so the energy is sufficient, then you have a self-commutation all the way from low to high in this particular case. This is the other way. I sort of changed the direction here. So this is another look at the same thing. This is the spikes that you have at the transistor, shown here, and this, of course, are very harmful. And here is a summary. What I'm showing here is the height of these spikes. Now, obviously, when everything operates fine, there'll be no spikes and this will be just the current of the normal current of the transistor, which is in this range. So we see that for this operating point, if we adjust the inductor to be 30 microhenry or higher, then I'll get soft switching. While if it'll be lower than that, I'll get hard switching. And again, I'm going back to this variable inductor. Could be very useful to indeed adjust it. So again, now let's go back to the question. Why can't I just use a very large inductor all the time? Okay, for that, I'm running here another simulation. I'm now going to show the following. The voltage here, the current, and the voltage here. Now, this voltage is the actual voltage and the actual duty cycle that operates this rectifier, not here. And the voltage at the input and the voltage here are not the same because there is a voltage drop across this inductor. Okay, so here it is. The border one is the input to the total transformer, and this is the active or useful duty cycle that you have. And this difference now is a function of the inductor. The larger the inductor, you need more time because change the current of the inductor, and the larger the inductor, it'll take more time, and then you'll chop more and more of the duty cycle. So large inductor is no good, small inductor is no good, and a variable inductor is a good compromise. So we see that the variable inductor could indeed be useful, and this is the whole idea that I'm bringing up here. Let me just emphasize that this variable inductor is an additional element. It's not part of the transformer. This is going to be a tightly coupled transformer, which will be of a higher efficiency because there is no leakage, and usually transformers which are tightly coupled have a higher efficiency. And this is an additional element. Of course, there is an economical issue here, but if there is a need for a very large voltage transfer ratio, then it could be a good solution. One side point here that many are maybe wondering, when you compare the two, I'd say, sort of best converters that we have today, the LLC and the phase shift full bridge, how do they compare? Well, there's a number of studies that have been done, and in general, you can say the following. The LLC has a little bit a higher efficiency, but the range of input to output voltages is wider with the phase shift full bridge. So if you have a situation, say a charger of a battery, that the battery voltage is changing, of course, and maybe the input is changing, so you have a range of input to output voltages that you have to handle, and then with an LLC, it might be more difficult than with the phase shift full bridge. So what are the conclusions here is, first of all, I hope that I've managed to show you that the value of this inductance is very, very important, and it affects the zero voltage switching and the actual duty cycle, and that the variable inductor can reduce the problem, can improve and make this envelope of operation larger. So this is the end of this presentation.